Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce James Hayes. He is a student currently at CMU and will be graduating in June. I think I first heard of your work when you started doing some repetitive texture work, but then recognizing it and then using it for different tasks such as in painting and texture synthesis. And then more recently, he's been doing a string of works using large image collections. So he has an in-painting work I think you're talking about today, and then also a work on localizing images using both scene recognition and feature recognition, which I think you're also talking about today. So
yes.
I'll hand it over to James.
Hi, thank you. And talking about a few other things as well. So I'm kind of covering maybe a little too much ground. If I'm going too fast over something, then just stop me and get me to clarify. Hopefully it won't be a problem. So our visual experience for us, our computers, is really extraordinarily varied and complex. Tons of different scenes and lots of complexity within any scene. And that complexity makes it really hard to understand images and to synthesize images. So in the computer, if you look at an image like this, just a snapshot I took, then there's thousands of meaningful image dimensions. There's thousands of things that you could want a computer vision system to answer you about this question, from what's the pose of all these articulated figures, to material properties, to illumination, to geometry. And most computer vision and also computer graphics techniques kind of get around this huge complexity by a divide and conquer technique. That is that the image isn't the representation, some part of the image is. So that something like sliding windows or part-based models, or segmenting the image first and then classifying segments. In the graphics community, they obviously tend to render things by building it up from part-based geometry as well. So all the work I'm going to talk about is fundamentally different. It's using scene matching instead to find information about images instead of going kind of into the image. And just one example of that to kind of show you what I mean by scene matching is scene completion, and this was at SIGGRAPH 2007. So let's say you have an image, a photograph you took, or something like that, and you want to remove part of it, or part of it is damaged, or you're doing a 3D reconstruction and you want to get a view of something that you never quite saw in the original views. So for whatever reason, you need to hallucinate some data here, fill it in such that it seems plausible, such that a human observer can't tell that anything was ever taken away. There's a lot of good previous work in this area. In fact, some of the people sitting here have done it. The simplest is just diffusion-based. Well, maybe I should ask for the lights to be brought down a little bit, actually. Oh, that's great, thank you. So diffusion-based methods just propagate color from the boundary of the region, maybe trying to preserve straight lines or something like that. But they're not preserving texture, so for large holes, it's not going to work reliably. Then there are texture methods, texture synthesis methods, a lot of them kind of following from Efros and Leong, that explicitly propagate texture from the rest of the image generally. But since they don't have any semantic knowledge of what the layout of the scene should be, they can run into problems as well, kind of blindly copying texture. It might be seamless and it might preserve textures, but they're just not in the right place. So this is actually a really difficult problem to complete an image. It's kind of a vision hard and graphics hard problem. You have to parse the scene and identify all the objects, even partial objects, and then render new objects on top of them with the correct illumination and viewpoint and things like that. So very hard. And what we're doing is trying to skip all of that and instead just find some scene that has as similar a layout as possible, as similar appearance and view parameters and high-level semantics, similar enough on all these axes that you can just steal whatever content is in the corresponding place and use computer graphics techniques to blend that in. And in this case, we can get a reasonable result by stealing a roadway from another image. It's not seamless. There's some blurriness, but it kind of got the vanishing point right, and it kind of, I think you wouldn't notice it at first glance. So the algorithm is pretty simple. The input image is actually an incomplete image. We never see the original one. And from that, we build a scene descriptor based on the GIST descriptor from Antonio Torralba and Ode Oliva, which is a measure of basically where the edge energy is in the image at different frequencies, different scales, different orientations. And then we have some color on top of that. Anyway, then we search a large database of unlabeled images from the internet, 2.3 million images in this case, and we find some nearest neighbors. And in this case, it works pretty well. These nearest neighbor scenes are actually pretty similar to the input. And for every one of them, we're going to try and find some alignment where they overlap best. They should be roughly aligned already because the scene matching tends to find similar layouts, but we can maybe improve it a little bit. And then at that best offset, we'll do a graph cut and Poisson blending to make it seamless. And in the case of this image, I'm walking too far away from that. Here's one of the scene matches underneath it. So it's overlaid. The incomplete image is overlaid with the scene match, and then after the compositing, that's the result.
So was that picture actually taken from the same location, the one that you found?
I don't think so. Actually, the hills are very different. I think it's a very different climate wherever it is. Similar camera height, I think, over the water. So, why does this work? We're not doing anything really smart to find similar scenes. If we have a small database of images, say 10,000 or 20,000, which isn't that small really, and we find the nearest neighbors using the same descriptor, this is what they look like. And they're not really that similar scenes. They wouldn't be useful for image completion, certainly. But with the database that's 2 orders of magnitude larger, then the scenes start to become similar, at least some of them, and useful for image completion. So, similar enough that you can use them for photorealistic image editing. So we're kind of getting to a point where we're sampling the space of images densely enough to do some cool stuff with millions of images. But if we go back to this image, we're never going to have enough images to be able to explain this with with an entire different image. I mean, this is so high dimensional that it's not just a rare image, it's once in the lifetime of the universe. This is never going to occur again. So if you want to know how many percussion instruments there are here or what the pose of the people is, you have to use deeper image understanding and go in there with part-based models or whatever you want to use. The idea with our scene matching is just to provide a much better starting point for all of those deeper image understanding techniques. And there's evidence that humans do exactly this as well, that humans use pre-attentive global scene features to help with things like object recognition. And further, Aude Oliva says that those pre-attentive features are memory-based. It's not that the humans are doing anything exceptionally clever about parsing the scene and helping to determine where objects might be. It's that they've seen similar scenes before, and they relate any novel scene to a scene that they've seen before, and thus they know, oh, these objects are likely to occur, or this is probably the correct scale that an object would be at, things like that.
So do you have any, you kind of said, when you small enough images, there's not one that matches. Do you have any way of telling or knowing whether there is a match, whether there is an image that is good enough? I mean, is there some sort of threshold? Or
I've certainly not found anything that's close to universal. Okay. I mean, the distances of the features aren't really comparable against different scene types. And small differences in distance make a big difference in the perceived scene matching quality in a lot of cases. So, no, I haven't looked into anything really like that yet. So the big picture is, for any image, we want to be able to use kind of internet scale scene matches to learn as much as we can, learn as much as we can from that, and then maybe that's a good starting off point for deeper image understanding. So to inspire the next project, I'm going to let Hollywood give the sales pitch a little bit. Let's see if this plays.
Pictures that were sent to the killer's phone.
Well,
and the next one's still a mystery because we weren't able to download all of it.
Look, do me a favor. Think you can dial us into where this is?
Oh, yeah. Larry and Amita have found a match for your photograph. There we go. I don't know the significance, but it's somewhere in the valley.
Wait, what? You're kidding. That's Robin's house.
What?
She's the next target.
So melodramatic when you only look at the clip. But so this is numbers, CSI-like thing where they've invented, this geolocation thing that actually, I want to pitch. So I want to try this. Given a single image, figure out where it is in the world. I should note that this was accepted for publication before that episode aired. let's just go through kind of at a high level how humans maybe geolocate images. I think there's qualitatively different ways that they do it. For images like this that are landmarks, both humans and machines have a pretty easy time saying where this is because it's visually unique and there's a lot of photographs of it or people visit it a lot. So it's not difficult to know that this is Notre Dame Cathedral in Paris. For an image like this, though, humans have a lot more difficulty. They can probably tell you maybe something about where this is in a generic sense, like this looks like the Mediterranean maybe, or Southern Europe, or some people say South America. For machines, it's possible that maybe instance level recognition could get this, maybe with enough street level views and the right matching and geometric verification, that there's enough discriminative stuff here going on that you could tell unambiguously where that is. But at some threshold, the world becomes too dynamic or noisy for this type of instance level recognition to work. Even if you had all of the coastline views of the world, I don't think matching SIF features is going to help you unambiguously geolocate this, especially if the data set is slightly out of date, because this is dynamic. The water changes, the beach changes, a hurricane hits and the tree changes. But a human can still tell you, oh, this is kind of tropical and lush. It looks like a warm environment on the water, obviously. So if you can't geolocate it unambiguously, you can at least narrow it down to a pretty small geographic area. So we're going to use scene matching, and so our data from the internet is 6.5 million geolocated images off of Flickr. This is just the distribution of them, and this is in log scale, so it's really quite a bit peakier even than it looks here. Some of the regions are pretty empty, like the middle of the Australian outback or Siberia. 110,000 different photographers, so that's an average of about 250 per photographer. And this is what a sample of these images look like. This is from our test set, actually, from the same distribution. Some of them are landmarks, like Sagrada Familia. Some of them are generic indoor images. A lot of them are pretty difficult to geolocate, and some of them are kind of dynamic scenes, like this glacier that are probably not going to exist in 5 minutes. And the features we're going to use the same as the scene completion paper that I just talked about. And I'm going to try and add some other ones. This is kind of a good task to quantitatively evaluate these different scene matching features. Color histograms and texture histograms, and also histograms of straight line features, like where straight lines are facing and how long they are. And then we also tried geometric context, which is the probability of each segment being ground sky or vertical. And we also tried tinier images, like tiny images like Antonio Torralba, except even tinier. And they're grayed out because they just weren't useful in conjunction with the other features. So in the end, I only use those 4. So I'm going kind of fast, sorry. So here's an example of what the scene matches look like. Very nice. Architecturally, they're very well correlated. The viewpoint is very well correlated. But also the location is correlated, at least among these scene matches. You can see that they're mostly in Europe. And if we plot these on the globe, we can see that this looks pretty different from the prior distribution. There's almost no matches in the Americas, and there were no matches in Asia. It's all centered on Europe. It's not doing a great job of telling where in Europe exactly it is. The ground truth is here in Barcelona, and it has some scene matches there, but it has them in other European cities as well. So it's at least giving you some signal. For this landmark images, our features aren't really suited to instance level recognition because they don't have any viewpoint invariance, but or not much at least. But there's so many images of something like this that you can still unambiguously tell that, oh, the biggest cluster of images is right there in Paris. And then for this more generic image, the scene matches, I think, look reasonable, but geographically, it's very distributed. Hawaii, Thailand, Brazil, Mexico, New Zealand, Philippines. I mean, I think they're mostly plausible, but geographically, they're kind of distributed all around water and the equator. The correct answer happens to be Thailand. And in this case, we do happen to have the most matches there, but it's kind of just a little lucky, I think. And then one more result. This is somewhere in the American Southwest. And I like it because the scene matches, it does a very good job, but again, none of them are actually matching this exact viewpoint or this landmark. They're finding some other landmarks that are similar to it, actually, but it's kind of identifying that there's something geographically discriminative about the texture, it's the rock formations. So it's pretty well peaked in the American Southwest there. So quantitatively, we can say that for about 16% of that test set, when using the full data set, about 16% of them the first nearest neighbor was within 200 kilometers, so it's kind of like within the nearest major airport or something. And as we decimate the data set, we can see that the performance goes down to chance, which is 1% in this problem. So 16% is not great in absolute terms, but it's a pretty hard test set. And I thought it might actually be pretty difficult for a human to do this. So I've done a small pilot study where I asked people, here's the test set. Tell me where each of these images is. And these are different human subjects, their performance, and compared to IM to GPS. There's a large variance. It depends a lot on people's exposure to international travel and things like that. Some people really don't recognize any of the landmarks, can't reason about some of the subtle things in the images, and don't do well. But some people do manage to beat the computational baseline.
So from your experience, the 16%, are they landmarks, or are the ones that
they're half landmarks, and then they're half other things like?
Is it just it's kind of like, since there's the most desert photos that exist on Flickr are Southwest photos, that you have a tendency to have the peak around the Southwest and fix that. Even though it's not exactly a landmark.
Yeah, I mean, it's something geographically discriminative. I think you could find another type of desert image that would not match well to the American Southwest. So it's not. I think it's not just at the level of classifying it into a scene type like desert or mountain. It does a little better than that. But it could be other things. It can be, there's pictures of the Greek islands I'll show later where the white, all the white buildings and the rocky ground is pretty geographically discriminative, I guess. So even without a landmark matching, it can tell that that's Greece. So it's kind of interesting to look at the images which the humans did maximally better than the machine. And I mean, a lot of the reasons are pretty obvious. Is that the humans can read the text and then know where that is roughly. And then here, I don't think it's the text, but if people know that these are London cabs, then it makes that pretty easy. And then also interesting is the other way around. The images for which IMT GPS did maximally better than the humans. So in this case, it's not because the humans don't understand the scenes, obviously. It's because, well, they know that that's probably Africa. They don't know where people actually go on safaris in Africa. And here, I don't know, does anybody know where that is?
South Dakota.
No.
Turkey.
Turkey, okay, well done. Yeah, and this is in Kenya. Almost everybody goes on safari. Yeah.
It looks like Cappadocia, is it?
So you have a different database.
Yeah.
And this one is in Kenya. Almost everybody goes on safari in either Kenya or South Africa. So it's actually not that hard to guess. So for most of the images, the geolocation is not really accurate. Here's another set of scene matches, and the scene matches are pretty good, but geographically they're all over the place. In fact, this image is in Morocco, and really almost none of the scene matches are there. But this can still be informative about the original image. If we, for instance, have an additional source of geographic information, like a map, and we sample that at the locations where we thought this image might be, then we can get an explicit estimate of whatever geographic property. In this case, I'm showing how hilly it is. It's the gradient of elevation. And we can say, oh, this is how hilly this image is, we think. Remember, the image is unlabeled originally. We're kind of just going through geolocation as an intermediary to get to whatever other metadata. We can do that for the whole test set, and this is what it looks like if you sort all of them by how hilly you think the images are. And I think it does a pretty good job. You get the mountains in the top, and then these are the bottom ones. And they're mostly urban images because a lot of big cities are in flat areas. And I mean, you can do that for any map. If you have a map of land cover, then you can kind of do scene classification that way. Here's the most foresty images. That means that they were geolocated to be in the most foresty regions. And these are mountains, but they are forested, so that's correct.
You only show day images. Is that a coincidence?
There's a night image here.
Oh, really? So there's less night images.
I guess. I mean, that's just the proportion of images people take. All right. So in summary, this data-driven scene matching, I think it makes kind of an interesting baseline for this task, and I think there's a lot of room for improvement. And even if we can't geolocate it accurately, then it can still tell you something about the image, just because the GPS gives you access to a lot of metadata, basically. So this is now moving into a work inspired by IMT-GPS, maybe kind of an extension. Again, so here's an image which I think is very generic. Somebody can impress me again and tell me where this actually is. It's meant to be confusing.
Paris.
No? Okay, so nobody knows. Good. What if I show you this image? Everybody should know where that is, more or less. It's in central London. But what if I show you these images together and have timestamps on them? And I tell you they were taken by the same photographer. Well, then you can reason that, okay, these are only 45 minutes apart, and this one's in central London, and you can't really get that far away. So, okay, that one's probably in London too. And if I add another image, okay, so this one, you can tell it's not in London, but it's a day after the other one. So if you're really trucking it, you could be almost anywhere on Earth. It could be, Rio, it could be Barcelona. So to help answer this, you might want to know, what are the likely locations that somebody is going to go to from London. So this work, image sequence geolocation, which is with Olga Veselova and Aaron Hertzman, and I should give them credit for doing most of the work. It's their idea. This work aims to take, just a folder of photos from your vacation. Say, okay, this is my vacation, or this is my entire photo collection, and they may or may not be from the geographically same place. In this case, there's some from China, and then we move to London, and then the Greek mainland, and then the Greek islands. And we want to geolocate all of these. So the inputs are images and timestamps. And timestamps aren't really trustworthy because maybe you didn't change your camera time to the right time zone, or maybe you never set the time in the first place, or the battery died, or whatever. But the differential between pairs of timestamps should be accurate for the same camera, even if the absolute time isn't. And this is really all we need. So what we're going to use is the time differentials between pairs of photos. And the goal is to geolocate all of these. You can describe this with a hidden Markov model. So what we're interested in, the location of the photos, and what we get to observe are the images taken from those locations and the differentials in time between the pairs. And this relationship is kind of explained by IMT-GPS. So I'm not going to go into that, the relationship between locations and images. The interesting new thing about this is this, which is how likely are you to move from one location to another in a fixed amount of time? How likely are you to go?
So when you showed us that what you know are the top and bottom rows, that's during the inference or test phase, right? During the training phase, you know the locations as well.
Right. That's true. I don't think we necessarily have an explicit. We don't have a training process that takes advantage of that right now necessarily. Well.
You don't look at the geo tags in your training.
So. Well, of course. When we learn this movement model, we do, right? Right.
I mean, that's nothing surprising there, but I just want to be clear, right? That the missing data, the hidden data is the middle row, but during the training phase, that's what you know, and that's how you learn.
Exactly. Yeah. That's true. So yeah, again, what this relationship is kind of encapsulating is, okay, I'm in London. What's the chance that I'm in Barcelona in 6 hours, or something like that? That type of probability. And there's a lot of related work on human movement from other fields. There's some publications in Nature recently where they, for example, track dollar bill serial numbers to see, and use that to infer where people have moved around the country. Or in this case, they're tracking people by cell phones. Neither of these covers international travel. And what they're kind of more interested in is coming up with a compact parametric description of how people move. They hypothesize that people follow this levy flight distribution where it's a power law distribution where they have lots of short trips, but the occasional, really long trip. It's a heavy tail distribution. But I don't think that simple parametric models are going to be necessarily that useful, because human movement patterns are really complex. Your movement will look different if you're in Jacksonville, if you're in New York. And we're going to try and learn it from Flickr data. And more recently, this group from MIT, the kind of urban planning group, has done the same thing where they take Flickr geotag data and look about how people move around a city. And we're going to do the same thing on a global scale, basically to say, okay, how many photographers move from Sydney to Hawaii in X hours? So we've discretized all the locations of the globe, and we've discretized time also. And this is the type of model that we learn, or this is a visualization of the model. That is to say, if you're in Honolulu and 0 to 5 minutes have elapsed, this is the probability of where you're going to be next. All right, so it's pretty stationary, right? 30 to 45 minutes, an hour to 2 hour. You're still in Hawaii, or you're in an airplane not taking pictures. 6 to 8 hours, a couple of people have managed to land and take photos of the airport or something. And then as you extend time over longer time periods, it starts to resemble more the prior distribution of the data. In general, it is more stationary than I expected. Even after 60 days, you know, a lot of people are still in Hawaii. They're very lucky people. So using this model and IM2GPS, we can do, you know, find the maximum likelihood path over the globe for a sequence of photos. And I'll just show some preliminary results for that.
So you go to Flickr, you download, you know, all the photos of some person, and you see that it's the same camera and you have the same timestamp, and so you assume, okay, this is evidence of where that person has been, right?
The only restriction is that it's the same person. We don't look at the camera or anything. We assume that a single Flickr user has taken all the photographs that he's posted.
There's lots of groups that, you know, have, well, actually, maybe it doesn't work like that. Okay, so, okay.
The photos are geotagged, or are you using the GPS to obtain?
We're using the real geotags to train the movement models. And yeah, and then given a new sequence, we're using IM2GPS to get a distribution like this, and coupling that with those movement models to help refine them.
It doesn't really matter that it's photos anymore, it's just sort of checking with the GPS tag, right?
Sorry?
It's just, you're just using the EPF location, you aren't using the fact that they're photos anymore.
Well, I mean, once IM2GPS has given you a geolocation distribution like this, then yes. Are we talking about training phase or testing phase? Or?
I guess the graph that you showed,
yeah.
This is just using GPS, right?
Right. This is just GPS. This is just the movement model. So yeah, just.
Is IM2GPS used for?
Oh, that's just what I talked about just before this. It's just given a single image, give a geolocation.
But in this context here,
Oh, well, given a novel sequence, I mean, you have to start with kind of the unary, whatever, probabilities of where you think this image is. In this case, it's a very bad estimate because it didn't do a very good job. But you know, IM2GPS provides this distribution. I go on to the next image, and then IM2GPS for this sequential image. IM2GPS provides this distribution, and then with the movement model, you're going to help refine those, find a maximum likelihood path. Anyway, so here's these results. Yeah, it doesn't do very well in this. The scene matches aren't actually that bad. It's just finding Chinatowns and other cities. It's actually in Beijing. But okay, this is the posterior or whatever. After inference, this is kind of the probability that it assigns to each location. And now the maximum likelihood is here in Beijing, and that's because the other images that were in Beijing that were close to it temporally were kind of more landmarks. And this one is more obvious in Beijing, but also some confusion with Hong Kong. The other one was a landmark. And moving on through the okay, this is after inference. Moving on through the sequence, this is the IM2GPS, you know, just the single image geolocation estimate for this one. So it's I guess, the best one in the sequence, the most landmarky one. It's Tate Modern in London. And then that helps. Okay, this is after inference. It knows it's in London, not surprisingly. This is the next image, the generic one that I showed you. And again, you know, I mean, the distribution here is just basically random. It's the prior of the data set. But since the previous one was in London, it knows that that's where it actually is. And since the next one is kind of a landmark as well, although there's some confusion with New York, then you know, it knows it's still in London, although there's some confusion. Anyway, moving on to this one. So this picture was actually in Athens. IM2GPS does a very bad job. It confuses it with Italy and Barcelona. And for that reason, you know, the inference isn't going to move it to Greece, really. It just leaves it in London and then decides that the next photo now is in Greece. This is after the inference. There was another day that passed between these pairs of photos, so the temporal constraints weren't helping that much. Then it has more pictures here on the Greek mainland, and then they move to the Greek Isles, and it did actually make a movement there. I'm sure. So anyway, out of this sequence, all of them were geolocated accurately except for that one. but it's kind of brittle right now. Like if I take these landmark images out, then all of these are wrong. It thinks you went to Beijing and then New York and then Greece and then the Greek Isles. So it's nothing, it's pretty intuitive, right? It's using the landmarks to help support the more ambiguous images that are temporally nearby. Any other questions on this? Okay.
Had any, I'm trying to get a sense for how helpful it is to have the training data rather than just a kind of generic smoothness prior.
Yeah. I thought the training data would be a lot more useful, but then actually playing with it, I'm not sure how much more useful it is. It's something we'll have to quantify when we actually publish it. Yeah. I think, yeah. I mean, I thought, yeah, I don't know. It's a very good question. It's not clear to me either.
It's also possible that there's a factor model that captures a lot of this, right? Because when you looked at Honolulu, it wasn't just radial distance, it was sort of radial distance multiplied by population density. Right.
It's multiplied by the prior, kind of.
Or by prior, right. So if if you're going to test if you're going to test the sort of data-driven model versus a parametric model, that would be the natural one to,
I agree.
To try.
I agree.
But then, you can also make up other hypotheses. Like you say, well, maybe nationality makes a big difference because Chinese people have a hard time getting visas to go abroad, right? So then national balance.
And that's what I was thinking. There would be more subtle things like that, but I'm not sure that we have enough data for those to really emerge.
If cameras recorded time zone information, and if that could be an additional constraint, so if people actually did change the time zone.
Oh, well, yeah, I mean, if they were explicitly changing the time zone and not just the time, then that would be super informative, right? I mean, that would be a huge constraint if it told you what 24th of the globe you're on. But they just changed the time. It's not clear if they're in a different time zone or if that time actually elapsed in the same time zone. Okay, so this recent stuff has been about finding geolocations for images, and some people have given me a hard time saying that this is not computer vision. John Ponce was very critical of this. So I wanted to show that these geographic estimates are useful for something, some core computer vision task like object detection. So working with Derek and Santosh, Derek is a professor at UIUC now, and again, they did most of the work here. I'm just going to talk about what part I did in this. And the idea here is that there's been a lot of investigation of context in computer vision, using context to improve, say, object detection. But the best performers in the Pascal VOC challenge are all context-free. Things like, or they were last year at least, all these part-based models from Pedro Felsenschwab, David McAllister, and David Ramanan. Works really well. Doesn't use any context, no scene-level context, no object-to-object context. And we thought, well, if we can add some scene-level context on top of this, surely it will improve the performance. So that's exactly what we're going to do. We're going to take their base detector exactly as is, not even retrain it, and get candidate detections, and then use context cues, from what we know about the scene to say, this is likely to be a cat, this is likely to be a cat, this is not likely to be a cat. And then there's also another part of it, which I'm not going to talk about, is then resegmenting based on those potential bounding boxes to improve the bounding boxes. And that ends up helping a lot. I'm not going to talk about that. So here's the top 5 cat detections from their detector, their local detector. This is kind of unfair, because their detector actually does a pretty good job in general, but for cats, it's just not so good. So these are confusions that shouldn't happen because the context is not even reasonable. Like, a cat can't live there. You should know that's not a cat detection. So the type of context we're going to focus on is, given an image, what is the probability that it contains a cat or a chair or a dining table or whatever object? And to do this, we're going to use similar features that I already talked about, to scene-level features, like the gist descriptor or the geometric context of this. We're also going to, we're going to try and learn the relationship between these features and object occurrence, not using scene matching, just directly from training from the Pascal training data, which is about 4,000 images. Trained to learn that, oh, this type of gist descriptor means cats are present. And then at the same time, what I did was use scene descriptors to go out on the internet, find similar images, find the most similar matches, and then use the properties of those scene matches to try and say whether or not there's a cat present. So I've kind of got this baseline scene level context to compete against. So the type of context that I'm getting, so this is an input image, and say this is some of the scene matches, not great in this case, but the metadata associated with them, like say squirrel or lion, could be useful in saying whether there's a cat there, and also the geographic properties. These are all geotag data, so we know exactly is this a grassland or is this urban and high population, things like that. And we can hypothesize that maybe that correlates with object occurrence. Maybe pedestrians are more likely in high population density, things like that. We don't use geolocation explicitly, just the geographic properties derived from it. So the actual features we build from this are a histogram of keyword categories, saying like, okay, in the scene matches for that query, I had 4 animal keywords, and that means it's likely to have contained a cat. And then we also have geographic features. That is, the scene matches had this population density on average, so, and maybe in this case, it's not very informative about whether or not there's a cat there. This data is, of course, extremely noisy. I'm relying on people from the internet to have annotated their images, and they don't use the same vocabulary. The scene matches only average 1 keyword per image, so it's not densely labeled like the Pascal training set was, which was perfectly labeled. All the objects are identified. And what I just talked about goes into a final regression to rescore bounding boxes, along with some other types of context that I'm not going to talk about, as long as the local detector score. So that is to say, we're rescoring every little box that the original detector found. And after we do that, here's the 5 most confident cat detections instead of these. And okay, so we do a little better. There's 2 cats instead of 1, but the confusions are a lot more reasonable. They're in settings where it could have been a cat. But this confusion happens a lot. And in fact, I think Pascal is intentionally constructed such that you can't use context alone to solve it. Here's the precision recall of the cat class. When we've added context, we get a big jump versus the baseline detector. Overall, it's a lot more of an incremental increase. In fact, there's not much of an increase here in this low recall regime, only kind of when we maybe get to the more challenging ones. I think this is kind of consistent with the work that Larry has done that says maybe the context is really only necessary when you get to the kind of the more borderline cases. But if you have a high resolution object, then the appearance alone is definitely unambiguous. And here's some more quantitative results. So our goal was to improve this baseline detector. And if you just look at the bottom row, this is average precision. And we go from 18.2 to 22 overall. So that's a pretty significant increase. But most of that increase is actually coming from fixing the bounding boxes using segmentation. The scene context only actually got us 1.2%, which is a little disappointing. Larry said that this was kind of a negative result, which I kind of sort of agree with. I mean, we could have maybe done it better, and we're only using one type of context, scene to object context. There's other types of context, like object to object context, but that was a little bit disappointing to me.
I think, so bicycle performs so much better.
I think it's hard to read too much into these. Average precision is kind of, if you switch the very first detection from incorrect to incorrect, the average precision can jump a lot. So it's kind of noisy measure, actually. I don't want to read too much into these. There's not a whole lot of consistency on what we do better on. Is it indoor or outdoor? Is it animal versus non-animal? I mean, we kind of do just slightly better on a mix of things. My contextual features are, I think, worse for indoor images because the geography is more ambiguous then. Here's the relative weight that the regression assigned to each of the scene level features. And I'm just going to block those out because those aren't dealing with object presence, they're dealing with object size and location. So these are the ones that are determining whether or not an object is present in an image. Here's an image, what's the likelihood there's a cat in it or something like that. And this is the relative weight assigned. So the presence column, that's referring to the gist descriptor and the geometric context as kind of trained within the Pascal data set alone. And then semantic context refers to the keywords from the scene matches, and geographic context refers to the geographic features from the scene matches. So these two really dominate the scene features that are learned from within the Pascal data set, which is somewhat surprising. I'm happy about that because it's the data set, learning within Pascal, that makes a lot of sense because the labeling is very clean. You can trust the labeling completely. And if you go out to the internet, you have so much noise to deal with. But the scene matching is so much better that it actually makes it worthwhile. You can really trust that the scenes are similar and that the properties, are more likely to be shared.
That scale varies significantly within object categories, right? The backgrounds and how they.
Oh yeah, it's a very diverse set of images.
Yeah, so it's really hard to do scene level.
Yeah, exactly.
Just from those images.
Right. You might. Yeah, I agree. And we entered this in the VOC 2008 challenge, and we get to put in our own little special box because we're the only people to have trained with outside data, and we're the first person to enter this competition ever. But I think it's okay. We can compare to these people who are doing the same task but only training within the Pascal data. The external data we used was only my scene matching stuff, and also because we used the 2007 version of Pedro's detector, but that's not really an advantage. So we did best in 6 classes, second best in 6 classes. So we're competitive with the best of them. So yeah, I mean, that's not bad. Any questions on this before I move on? All right, so changing gears a little, something ongoing work I'm doing right now is high interest photo selection. I was hoping Jan Key would be here because this kind of relates to his work a lot, his past work. So my motivation is that computer graphics does a lot with post-processing images. That's the justification for a lot of the imaging track of SIGGRAPH. Oh, we want to fix this image in one way or another. But I think that a photographer creates a great photograph mostly at capture time and not as a post-process. I mean, there's a lot of things you can do at post-process to help, but some examples of good photos. I mean, things like this don't happen because you post-process them correctly. They happen because you were at the right place at the right time and you were taking pictures, a lot of pictures. So I think we should really be going crazy at capture time as photographers. I mean, an iPhone holds 20,000 photos. Digital cameras are really fast. Memory is really cheap. But we don't do this, or at least I don't do this, because organization becomes such a hassle if you have that many photos. I've taken, on my SLR, the click counter is up to 50,000, but I haven't posted photos in 2 years just because it's so hard to go through all the photos and pick them out and things like that. So a little help and maybe suggesting that these might be the nicest photos to share, I think would go a long way. And this is a quote from a professional photographer saying, if you get one good shot on a roll of 36, so this is from the age of film, you were doing good. When you edit ruthlessly like that, people think you're better than you are, a better photographer than you are. So this is kind of saying the key to good photography is throwing away most of your photographs, which I also kind of agree with. You have to be very selective. So the goal of this project is, given some collection of photos, whatever, your vacation photos, to automatically suggest that, okay, these dozen or so seem, really good. Maybe you could share these. And then you can, throw them up on Facebook without thinking too much. And this is an application that requires, or at least would like, high precision, but tolerates low recall. We're only grabbing a few of the interesting photos out of a larger corpus, and maybe it's okay if we miss some interesting ones and leave them unchosen, as long as the ones that we do pick are good. So what makes a photo good? That's very difficult, right? There's not a single objective measure. People could argue about it. And there's photography rules that you can reference, but they're scene dependent and they aren't set in stone. For example, you can go to a website trying to learn to be a better photographer, and it will say the 4 rules of composition for landscape photography. It's scene specific. And these rules might not be specific for portrait photography or macro photography or architectural photography. In fact, like framing images, I think that's probably a great piece of advice for landscape images, but for other scenes, it could make them look kind of cluttered. And any guidebook like this is going to say, the rules are meant to be broken anyway. It's kind of nice to know these, but they're not set in stone. So I think a nice way to try and evaluate how interesting a photo is or how good a photo is just to find similar scenes and say, okay, what did people think of those scenes? They've been up on the internet. How many times do people click on them and things like that? So we're going to do that using the IM2GPS database, which was 6.5 million images. They happen to be geolocated, but we're not using that here. And then I added 600,000 more photos, which are the most interesting photos on Flickr. That's the 500 most interesting for every day of the last 4 years. And then the pieces of metadata that might be relevant for determining whether a query was interesting was that for each of these Flickr photos, we have an interesting rank, this rank, something of the form of, it was this rank out of this query segment. We don't have like a real valued number for interestingness, unfortunately. Flickr hides that. And then we also have the number of times it's been viewed, the number of tags, number of words in the title. Those might be correlated with increased quality if people are more willing to label it. And for a query, we're just going to assign, the features we're going to assign to it are just, how interesting are your scene matches? How many views did your scene matches have? What's the number of tags in your scene matches? It's a little more complicated than that, but that's basically it. And there's also how far away you are from your scene matches. So these are all scene matching features, and then as kind of a baseline, we're going to add to these the features that Jan, who's here, developed for photo quality assessment, which is probably a pretty similar task. And I'd say these are kind of lower level things. Does the image take the entire dynamic range? Is it well saturated? Does it not have too many hues? A narrow band of hues is actually positively correlated with quality, things like that. And I'm going to define a test set from the internet data. I'll just kind of skip over how I'm doing that. But here's an example of positive images. So these are images that should be determined to be high quality or interesting. And I think, okay, yeah, that's pretty reasonable. One of the problems that we run into a lot is this, what's going on here is that the high quality photos often have a lot of post-processing, and that's not useful for this task because we're trying to look at photos right off the camera, for instance. And we don't want to learn that post-processing is good because none of them will have post-processing. But maybe they're post-processing it in a way that's, that a camera could produce, not in this case. And here's the bad images. These images all have 0 views. Nobody on the internet ever clicked on these Flickr images, which means that by building this data set, it's a destructive process. These images no longer have 0 views. So this is a high quality. I mean, I think I like this image. I think some of them are fine. Maybe this one's okay too. Maybe a little too closely cropped. I don't know. I mean, this is a problem. There's a lot of reasons an image could have no views. They're all publicly available, but maybe this person just doesn't have a lot of friends looking at their album. Or maybe they posted a string of redundant photos and nobody bothered to click on the third one that was similar. I don't allow photos from the same photographer to appear multiple times. So I already went over the problems. So we have a test set, and we use just a linear SVM to find weights for those different features I showed you earlier. And here's the results. So this is kind of the baseline, which is actually a very good baseline because Jan's stuff works very well. This is using his features. These are just derived from, from the individual image, not using scene matching. And this is the precision recall for the task. These precision recalls are higher than I thought because I thought the test set would be very difficult to separate the positive and negative classes. And it's pretty hard, but they actually do pretty well, especially in this low recall regime. So Jan's features get about 80%. Mine are up here, and then if we combine them both, then we're getting like 90% precision out to 20% recall, which is...
If you're testing data set, is it the Flickr photos that you're testing on? So
yeah. No. Oh, yes, in this case, yeah.
So is the images then, they have post-processing?
Yeah.
So do you know if you might be learning a post-processing detector rather than a...
I think that's part of it, yes, unfortunately.
So remind me what your scene match features does.
So, okay, given a query, it goes find scene matches, and then for those scene matches, it's looking at, what were the interesting rank of those scene matches, how many views did those scene matches have, things like that.
So you're saying your scene matches are basically trying to find things that are geographically similar.
Well, I mean,
or just similar in layout.
Yeah, I mean, we're using the same features that we used for the geographic task. That's true, but this is just kind of another axis that we expect the scenes to be correlated on, and they are. Matching scenes are geographically correlated. They're also quality correlated, it turns out. Not surprising, really. Yeah, I mean, we should, yeah, so you're talking about the features used in the scene matching, and those were the same as IM2GPS, right?
I'm just trying to get an intuitive understanding for what's happening. Like with Jan's, you just reminded us that there's brightness and blur and things like that, color entropy. But for yours, you're using GIST and what else? Some color histograms, texture histograms. But you're using those features, or you're actually going out and matching against?
We're going out and matching. And the features that go into this are the features derived from the scene matches.
Right, so you go out, you find the closest matching images, and then those have all been tagged by their relative interest? Or
Well,
a small subset has?
they all have the metadata. It's not something that, it's generally not something that users are explicitly tagging. Like the interestingness is, Flickr doesn't say exactly how it's calculated. It's proprietary, but it's derived from viewing habits of people.
So and then you're training a regressor, which will, based on those things like number of times views, tries to predict how interesting the
query image was. Yes.
The query, right. Well, the query image generates a couple of matches, and then you're trying to find a score.
Yeah, I guess we could say we score the matches
You're
first.
learning something that maps and match statistics, view statistics to interestingness. And that training is based on the ones which were actually that 600,000 subset, right, where you know that these are interesting.
The training process happens after the scene matches are collected. Okay. So
what are the labeled examples that go into that training process?
So again, this is from the, whatever, it could be the training or the testing set.
Okay.
So what are the labeled examples?
So these are things you thought were interesting based on what?
Well, so I tried to pick out a test set.
Oh, okay.
Some that had a lot of views and some that had no views, and some other properties. Okay. Anyway, so there's the performance, and if we look at what the SVM is, how it's actually weighting the features in the combined classifier, you can see it's about half of Jan's features and about half of my scene matching features. And so things like the number of tags turned out not to be useful, or it might have already been encapsulated in the Flickr interestingness score. Increased distance to your scene matches is positively correlated with increased photo quality. I guess maybe that's capturing something like if it's a unique photo, that's better. So to make this an actual system, like you give it to a user and they pull photos out of the collection, the one last thing you need is to suppress redundant photos if they're really taking a lot of photos of the same thing. And we do that just by clustering and taking only the best image from each cluster. So here's some qualitative results. This is Alocia's pictures from Paris, and this is random samples of them. So it's kind of a lot of urban architecture photography. Also, here's some more samples, a lot of portraits. And yeah, it's about, I think almost all of the computer vision community is in here at some point. So here are the most interesting photos that it finds. And some of them I think are okay. I like the black and white ones. Does anybody know who that is? Yes. How did you know?
Oh, he gets a haircut at least.
The vegetarian pride thing. But I don't think these photos these are definitely not good photos. So I think it's kind of capturing that, oh, they're really saturated, or oh, they look like they've been post-processed to some degree. Here's the next set of 12, the 12 next most interesting ones. I think actually some of them are better here. I like most of these. I mean, this is a little pedestrian, and maybe that's a little cluttered, but pretty good, I think. I mean, different people might have different takes on it. Here's the least interesting photos. Again, they're all gray, so you can see that saturation plays a significant role. The next 12 least interesting. One last thing to show is that if you have an interestingness assessment that's working well, which I'm not sure that I do, then you can use it as an oracle for some other image manipulations, whatever it is. I'm just going to show with cropping. That is, here's an original image. Let's generate lots of crops. Let's pick which crops are the most interesting. And these are the 12 most interesting, and some of them are, these aren't good, clearly. Some of these are okay. Here's the 12 least interesting, which, okay, this one's actually maybe okay. I think this task is harder when it's only doing scene matching based on parts of a single image. The scene matches might not change that much.
The whole group's devoted to minimalism in photography, and they might argue differently.
Yeah, so, there's this whole thing, like, if you're a good photographer, this isn't for you. Right? If you actually have a message to get out there, then this isn't for you. But this is based on the consensus of the internet crowd, as dumb as it might be. But I mean, you can disagree with what it thinks is interesting for the test set, for example, but you can't really deny that that's the consensus of the crowd for whatever reason. Even though experts could definitely disagree with this. All right, so this is a work in progress. I was kind of aiming for SIGGRAPH, but the results weren't there. So if anybody has feedback on any of this, I'd be welcome.
One phenomenon I've noticed on Flickr is that certain photographers get a following.
Right, this is a social thing.
No matter what they post,
exactly.
They get thousands of views. I just can't believe some of the stuff they post gets all these positive reactions.
Exactly.
And I don't know how to filter that out, because I'm like, I look at their work, and like everything they post gets 100. And they just seem to go out and try to collect friends.
Yeah, I thought about trying to normalize by photographer to say that this photographer, all of his stuff seems to get views, so maybe you can't trust that. But then maybe you do want to trust that. Maybe he's actually a sincerely good photographer.
He's got some good stuff.
Right.
Establish that.
So it's hard to say. I agree.
Yeah, that for a reason, but then at some point along the way, it got less meaningful.
Yeah. And I thought about going to other data sets as well, like DP Challenge or Photo.net, where they have explicit ratings that are pretty reliable, I think. But then you have orders of magnitude less data. So it's not going to look like a scene matching solution at that point.
You can do a game like a label me.
Sure. In fact, Blues Went On has a game that's kind of in this vein where you're, I think, doing some sort of binary force choice between which photo you like better. But again, the results then are, I think, binary force choice. Like this person thinks this image is better. I think that data would be good to look at. I need to bug Luis about that. Yeah.
I think DB Challenge actually would be really useful for testing. And it wouldn't be good for training. There's not much data.
I did actually. I did actually test on there.
Okay. So you get similar results.
No, actually, I do worse, and Jan does about the same. So in fact, Jan's features do better. That's what he developed his algorithm on.
Yeah.
And I'm slightly worse. And if I combine them, I really only very incrementally improve his performance. So it's not clear. So yeah.
Instead of how many, it might be interesting to see who's giving positive feedback.
Yeah, I don't think I have access to that.
Have better taste than others. So if they're bothering to comment on a photo, maybe.
It may
look at the comments.
It's a vision thing, but you could do the social network analysis of it.
Yeah, you need a page rank for each photographer that comments.
Yeah.
It's a good goal to aim for the average user, right? I mean, you could be like a populistic artist like Miro, it's pretty good.
You want to be the most possible mainstream cliche photographer. Yeah. If you don't like the philosophical idea behind this, I completely understand.
I think, when you first talked about taking lots of photos and then having the system suggest the best one, because you have too many, I mean, I got very excited. I think it would be wonderful to develop such a system. It's just, it's a hard task, right? I don't know if the quality of your results or Jan's results, is the state of the art useful enough to deploy it today, or is it just not? It's a very subjective decision, but basically being useful enough means that for your target audience, which is the audience that doesn't have time to go and manipulate their photos or select them, not people like Fredo Duran, for the point-and-shoot crowd, would it be good enough that they would trust doing their triage to the system, right, where they would use it as something that suggests it? So, building the complete end-to-end system that includes the clustering and then suggesting. So you mentioned clustering has to be done. Did you do that as part of the photos?
Yeah. So there's still photos that look pretty redundant because, well, the clustering wasn't that extreme.
There were those two Notre Dame shots.
Exactly. There's two Notre Dame shots, and then there's also two of these shots. So so there's different aspect ratio. In this case, there's enough translation such that the descriptors are different. I mean, I tried tuning it a little, and I can get rid of those duplicates. Oh, plus these are duplicates as well, sort of. But again, they're different enough vantage points that they didn't cluster together.
Another thing you can do is do like an online version. You show this to the user, it clicks, he ranks, and you redo everything. You can think of like a more personalized system.
Right. Personalization makes sense, certainly. That would be.
Some people will be just like everybody else.
Yeah, Yeah, I'm not sure how to couple that personalization with the scene matching process. Or.
Well, you can see the simplest thing would be to seed the ranking with your database, show it to the user, get a re-ranking, and then you could even apply the SVM on that. It's the difference.
That's true.
But the post-processing issue is interesting too, because I've noticed a lot of photographers on Flickr post an image and then it seems really popular, and then they go and post the original, and it's like you look at the two and it's like, wow, I didn't even see that in that image.
Really?
I would have never.
That would be very cool to be able to couple those.
To post-process it that way. But
really?
It seems, yeah.
We need an image potential meter.
Is the one on the lower right tagged HDR? Because it looks very typical of the kind of extreme tone mapping with halos that people use in the
I hate
HDR.
this, but they love this. They love to show off their halos. I don't know if it's tagged with HDR. I didn't check. But yeah, it's not quite as pronounced here. But I'm not sure that people even, maybe they could have had the dynamic range they need with the original shot. They just exposure bracket and do this just because it's like the trendy thing to have. It's very much against everything that SIGGRAPH has been going for the last 5 years, which is interesting.
Yeah, I don't even know if the halos are qualitatively similar to just excessive unsharp masking, right? Because if you do unsharp masking, you also get that kind of thing.
Yeah, I think it's different. I mean, it's where they manually segmented out the layer they wanted, feathered a large amount, like with a radius of 100, and then composited.
Yeah, I think that's from an erase brush.
I think, I don't.
It might be.
No, I think it's from selection and feathering. I'm going to argue, but I could be wrong.
Yeah, same.
Another possible direction, if you're inclined to go that way, is to not exactly do what Louis does, because he always sets up games, but to basically release something on the web and then gather data as people use it, right? So you have your photo picker, right, and you release it as a little applet.
Like a service where they would upload their photos first.
Exactly. You upload it, or you point it at the directory. I think upload it, given it's a web thing like that, right? You upload your photos. Maybe it's good about uploading, small ones so that everything works fast, and it gives you kind of a little stack. Maybe clusters, and you'd have to think about what the services that you're providing. Right. But if you have it as a web service, then you could capture information, right? It would cluster things. It would give you your best ones. If a person wasn't sure that was the best one, they could go through the stack of things that were clustered and say, no, I want this one. I'm not sure. It'd be almost like launching a little product, but because you do it on the web, you can use it as part of your research because you get the feedback. Right? I mean, you can do that kind of thing internally by just having 10 of your friends use the system, or you can launch it as a service, run it for a few weeks, and see what happens. Right?
Or another suggestion in this direction, I think, you could, this image of the house is part of a cluster, right? And someone, you look at someone's picture and it looks at some picture on that cluster, but this is the most, highest ranked one in the cluster. You could tell the user, you could possibly, change your photo to look more like this, then you have lots of friends and fame.
Right.
Or here's a creative suggestions of manipulations to your photo.
Right.
Here are a few examples.
Right. There's the idea of forcing them to be more like the positive images, not just selecting them as they are. And like you suggested also, the idea of being able to learn the mapping between pre-processed and post-processed would be even better, but that training data has got to be hard to come by. Yeah, those are all good ideas.
Instrument something like Lightroom or Picasso or Photo Gallery. There you start with, users start with a huge collection of images and they upload certain ones. So that's pretty valuable information.
That's true.
Which ones were uploaded.
Yeah.
So you can instrument any of those applications.
I need a friend at Google.
Yeah, that's if you want the reach, but if you want to release it as a university research project, and it's kind of explicitly, this is a project, and if people find it useful, they can use it. And basically, there's implied consent there that you will keep capture this data. Right?
But if you don't think somebody with Google, like Google, would be comfortable with training from their data? I mean, is that an invasion of privacy to train from?
Remember Google?
I don't think you get data from that.
But you would have to be like interning there or something.
Yeah.
or post on?
I don't know. I mean, I know like the photo gallery, you can write your own plugin to upload, right? So you can imagine plugging in yourself. So you wouldn't even have to invoke the company's privacy policy.
And isn't it the case that with Google Images they preserve, with the Picasa web album, they preserve the rights to do anything they want with it, or anyone can download it?
I don't know.
Free or something. There was something like that for a while. Might be still the case.
Okay,
All right. Thank you so much.